Now we'll see the now in these two problems we have seen the procedure to prove that the transistor is operating in active or saturation by assuming it to be operated in active region. Now we'll see the procedure to prove the transistor to be operating in saturation or active region by assuming the transistor to be operating in saturation. And this uh, procedure itself has 3-4 questions which are asked in the gate examination, and also this procedure is a bit easier than the previous one. Procedure to prove transistor to be operating in saturation. This procedure is to be used as it is. First, assume transistor to be operating in saturation. If transistor is operating in saturation, we can assume these two values VB equal to 0.8 volt, VC equal to 0.2 volt for silicon. And if it is germanium transistor, these values will be different. This will be 0.3 volt and this will be 0.1 volt. Now in the second step, we'll calculate base current or it is called base current, or it is also called actual base current, or supplied base current by applying KVL in base emitter loop. In the previous problem also, when it is confirmed that transistor is operating in saturation, we have calculated this base current by applying the KVL in base emitter loop, and we got this value IB supplied, which was the base current of the previous problem. We got this value equal to 84 microamperes. Now in the third step, calculate collector current by applying KVL in collector emitter loop. Just now we have calculated this collector current IC by applying KVL in collector emitter loop. We didn't use this equation IC is equal to beta IB, and we have calculated this collector current IC equal to 4.9 milliamperes. Now in the third step, in the fourth step, calculate the minimum value of base current required for a transistor to be operating in saturation. Required for a transistor to operate in saturation. This minimum base current IB minimum or IB required minimum required current. See one thing, that this is not the actual flowing current, it is just a value which will be compared with the supplied current. this minimum base current which is required for transistor to operate in saturation is equal to IC by beta. And in the previous problem we have calculated IC by applying KVL in the collector emitter loop, which is 4.9 milliamperes, and beta was given equal to 100, so it comes out to be 49 microamperes. Now in the last step we have to just confirm that IB required, or sorry, IB supplied is greater than equal to IB required or IB minimum, or we can say that IB supplied is greater than equal to IC by beta. Remember, this is the base current which was calculated by applying KVL in base emitter loop, and this is the collector current which was obtained by applying KVL in collector emitter loop. We didn't use this equation IC is equal to beta IB, and this equation is not valid in saturation. So if we are able to satisfy this condition, then if transistor satisfy this condition, then it is operating in saturation, otherwise it will be in active region. This IB supplied we have already calculated, it was 84 microamperes in the previous problem, and in this the base required base current we have calculated, which comes out to be 49 microamperes, and we have this 84 microamperes greater than 49 microamperes. Therefore, now see this example which was asked in the GATE 2000 electronics paper. In the circuit shown in the figure, assume transistor is in active region. It has large beta and its base emitter voltage is 0.7 volt. The value of IC is this circuit is given, and we are asked to calculate this collector current IC. In this question, one thing is not given, that is value of RC, and options are indeterminate as RC not given. Option B is 1 milliamperes, option C is 5 milliamperes, and option D is 10 milliamperes. We want to calculate this collector current IC. This collector current IC will be calculated using the procedures we have seen up to now. Already this transistor is given in active region and VB is given 0.7 volt. This type of biasing, here we have shown, this type of biasing is called potential divider bias, and this potential divider bias can be converted into the simpler circuit which we have seen up to now. The circuit can be converted into this circuit. In this circuit, this resistance RB will be the parallel combination of these two resistances, R1 into R2 upon R1 plus R2, and this voltage VBB will be the voltage at this point, which is calculated by applying KVL, sorry, potential divide, by applying potential division rule in this network, in this particular network. It can be calculated as 15 into 5 kilo ohm divided by 10k plus 5k. So this value R1 in parallel with R2 will be calculated, and it comes out to be 3.33 kilo ohms, and this value comes out to be 5 volts. Now we'll solve this circuit by taking this resistance as 3.33 kilo ohms and this voltage equal to 5 volts. This voltage is given 0.7 volt. Now when we apply KVL in this loop, we get the equation minus 5 volt plus IB into RB plus 0.7 volt plus, in this resistance the current will be IE, so plus IE into RE equal to 0. Now in this equation, if we want to calculate base current IB, it can be calculated, but there are two unknowns. One is IE and one is IB. We know that IE equal to IC plus IB. This can be written as beta into IB plus IB because transistor is operating in active region. So we can write IC is equal to beta into IB. So this will be 1 plus beta into IB. So IE is equal to 1 plus beta into IB. We can substitute this in place of IE. Now the above KVL equation will become minus 5 volt plus IB into RB plus 0.7 volt plus 1 plus beta into RE, sorry, IB into RE equal to 0. Now in this equation we have one current IB, but beta is also there in this equation, and in this problem beta is not given. As beta is not given, we cannot calculate the base current IB, and if we cannot calculate this base current IB, we cannot calculate the collector current IC. But still this problem can be solved because in this problem we have given beta is very large. Remember one thing, that if three conditions are given are in the problem, that beta is large, beta equal to infinite, and sometimes beta not given, if these three conditions are there in the problem can be solved by taking some approximations. That approximations are IB is equal to 0 and IC is nearly equal to IE. These two approximations will help to solve the problem. So whenever beta is given large, beta equal to infinity, beta not given, in these three cases we can take IB equal to 0 and IC equal to I, and can proceed for further solving of the problem. Now we'll start. Here IE is not given, sorry, beta is not given, so we will take IE equal to IC and we'll apply KVL in this loop. Now we'll solve this problem again. Now when we apply KVL in this loop, we get minus 5 volt plus IB into RB plus 0.7 volt plus IE into RE. But when we take approximation, we get IB equal to 0 and IC equal to IE. So this equation reduces to minus 5 volt plus 0.7 volt plus IC into RE. So IC can be calculated as 5 minus 0.7 divided by RE, which is equal to 4.3 volt divided by 430 ohms, and this comes out to be 10 milliamperes. So the required collector current is 10 milliamperes. D option is correct. So as beta was not given, we took two approximations and solved the problem. Now take one more example. Assuming VC saturation equal to 0.2 volt and beta equal to 50, the minimum base current IB required to drive the transistor in the given figure to saturation is we know that the minimum base current which is required to drive the transistor in saturation is IC required or IB required or IB minimum, and its value is equal to IC by beta. Here this voltage is given and VC saturation is given equal to 0.2 volt, beta is given equal to 50. Now when we apply KVL in this loop, we get the equation minus 3 volt plus IC into 1 kilo ohm plus 0.2 volt equal to 0. So IC is equal to 3 minus 0.2 divided by 1 kilo ohm. It is equal to 2.8 milliamperes. And now IB minimum base current required is equal to IC by beta equal to 2.8 milliamperes divided by 50, and it is equal to 56 microamperes. Now take one more example. In the amplifier circuit shown in the figure, the values of R1 and R2 are such that the transistor is operating at VB equal to 3 volts, VB equal to 3 volts and IC equal to 1.5 milliamperes when its beta equal to 150. For a transistor with beta of 200, the operating point VCE, IC is operating point VCE, IC is, and the circuit given is now in this circuit we have given this transistor we have given that the transistor has beta equal to 150, VB equal to, sorry, this is VCE equal to 3 volts, IC is equal to 1.5 milliamperes. Now for this transistor, this word use amplifier is used. If amplifier word is used for the transistor, it is confirmed that it will operate always in active region, because for transistor to be used as an amplifier, it should be used in active region only. The options given are 2 volt, 2 milliamperes, 3 volt, 2 milliamperes, 4 volt, 2 milliamperes, 4 volt, 1 milliamperes. Now we'll start analyzing this question. First, in this circuit, VC is given. We are doing DC analysis, so this capacitor and the circuit beyond this capacitor is of no use. VC is given equal to 3 volt and IC is given as 1.5 milliamperes. Now when we apply KVL in this collector emitter loop, we get equation minus 6 volt plus IC into R2 plus 3 volt equal to 0. Now R2 equal to 6 minus 3 divided by IC, which is equal to 3 upon 1.5 equal to 2 kilo ohms. Now R2 equal to 2 kilo ohm. Now in this question we have asked the operating point when we replace this transistor in the circuit with a transistor with beta equal to 200. The first transistor given in the circuit is with beta equal to 150, and when we replace this transistor with beta equal to 200, then we have to calculate this VCE and IC. Of course these two values will be changed and we have to calculate this changed value. Now once we calculate this R2, now we will calculate the base current IB. We know that the transistor is operating in active region because it is an amplifier. So IB equal to IC by beta will be equal to 1.5 milliamperes divided by 150 will be equal to 10 microamperes. IB equal to 10 microamperes. Now when we apply KVL in this base emitter loop, transistor material is not given in this problem. Now when we apply KVL in this loop, we get equation minus 6 volt plus IB into R2, because through this resistance base current will flow, plus VBE of this transistor equal to 0 volt. Now from this equation we get IB equal to 6 minus VBE divided by R2. Now again we will read the whole problem. That amplifier circuit shown in the figure, the values of R1 and R2 thus are such that the transistor is operating at VC equal to 3 volt and IC equal to 1.5 milliampere when its beta is 150. For a transistor with beta equal to 200, the operating point VC, IC is, means we are to calculate we have given that a transistor has beta equal to 150, then we replace a transistor with beta equal to 200. In this equation of IB, we have this VB 6 volt and this resistance R2. All the three values will be same even if we replace the transistor, because with replacement only beta will change, and in this equation we don't have beta included. So if beta is not there in this equation, IB will not be affected due to replacement of the transistor. So with sorry, this is the equation for IB. And now when transistor is replaced, now beta becomes 200. Even if beta is changed, we know that IB does not depend on beta. VB will be same for the new transistor also, because material will be kept same. R2 will be same. uh, R1 we have calculated earlier. This R2, sorry, this is R1, this is R1. And if beta is changed, with change in beta, IB will not change and IB still will remain 10 microamperes, but beta is changed. When beta is changed, IB is same. IC is equal to beta into IB will become 200 into 10 microampere will be 2 milliamperes. Now IC is equal to 2 milliamperes. This is 2 kilo ohms, just now we have calculated, and this IC is just now we have calculated 2 milliamperes, and this voltage VC can be calculated using the KVL equation in this loop. When we apply KVL equation in this loop, we get minus 6 volt plus IC into 2 kilo ohms plus VC equal to 0. So VC equal to 6 minus IC into 2 kilo ohms will be equal to 6 minus IC 2 milliamperes, and RC 2 kilo ohms equal to 6 minus 4 equal to 2 volts. So we get the answer IC equal to 2 milliampere and VC equal to 2 volts. Option A is correct. Now take one more example. In the circuit shown below, VB equal to 0.7 volt. And here is the question, that the beta and VC are respectively, options are given, 19 and 2.8 volt, 19 and 4.7 volt, 38 and 2.8 volt, 38 and 4.7 volts. These values are given and we have to calculate beta and VCE for this transistor. Whenever the combination of Zener diode transistor, Zener diode op amp, Zener diode FET is given, always start that this diode will operate in breakdown region and will have a constant voltage across it, that is equal to breakdown voltage of it. So at this terminal is grounded. At this point the voltage will be equal to 6 volts. Now for this transistor VB is given equal to 0.7 volt. Now we can replace this 6 volt with a battery, so we can apply KVL. As this is not a practical battery, but we are using it for just applying this KVL equation correctly. Now through this resistance the emitter current IE will flow. Now when we apply KVL in this loop, we can calculate this emitter current IE. So now we start minus 6 volt plus 0.7 volt, this is the solution, plus 530 into IE will be equal to 0. Now IE equal to 6 minus 0.7 volt divided by 530, it is equal to 10 milliamperes. Now once this current is calculated, we'll now calculate the other things. Now once IE is calculated, we know that IE is equal to IC plus IB, and IC is equal to beta into IB, so it will be beta into IB plus IB, it will be equal to 1 plus beta into IB. Now IB will be calculated as, sorry, beta is not given in this problem. We cannot use this equation, beta is not given. Now the current through this 4 kilo ohm resistance is, let's say, I. This current I will be divided into two parts. One is base current of the transistor, and this current is Zener current, that is 0.5 milliampere given in the problem. This I can be calculated directly. This voltage is 10 volt, this voltage is 6 volt. This I can be calculated as I equal to 10 minus 6 divided by 4 kilo ohms equal to 1 milliamperes. And I equal to IB plus IZ, and IB can be calculated as I minus IZ will be equal to 1 milliampere minus 0.5 milliampere, so IB equal to 0.5 milliamperes. Now we know that IE equal to 1 plus beta into IB, so IE upon IB will be equal to 1 plus beta, and we know both the values IE and IB. IE is equal to 10 milliamperes and IB equal to 0.5 milliamperes, which is equal to 20, and beta is equal to 20 minus 1 equal to 19. 1 plus beta equal to 20, so beta equal to 19. Now the second value will be calculated, but before that we'll calculate the collector current IC, which is equal to beta into IB, which is equal to 19 into 0.5 milliampere will be equal to 9.5 milliamperes. Now the rest of the calculation I will do here. Now in this circuit, collector current IC is known, emitter current IE is known. This value VC can be calculated by applying KVL in this equation. When we apply KVL in this loop, minus 10 volt plus IC into 200 ohms plus VCE plus IE into 530 ohms equal to 0. Now VCE will be equal to 10 minus IC into 200 ohms plus IE into 530 ohms will be equal to 10 minus 9.5 milliamperes into 200 ohms plus 10 milliamperes into 530 ohms will be equal to, this VC comes out to be 2.8 volts. So beta equal to 19 and VC equal to 2.8 volt. So option A is correct. Now take one last example. A transistor amplifier shown in the figure shown in the figure the quiescent collector current rounded off to first decimal is, the circuit is given. Now we'll start analyzing quiescent collector current Q point. The collector current at Q point is asked. So we will do DC analysis again. This capacitor will not be of any use. Now in this transistor circuit, the current through this resistance 4.7 kilo ohms will flow, uh, will be divided into two parts. One will flow in the collector terminal of the transistor, which is called collector current IC, and one will go in the base terminal of IC, which is called base current IB. So this current is the addition of IC and IB. Options given in this problem are 2.6 milliampere, 2.3 milliamperes, 2.1 milliamperes and 2.0 milliamperes. Now we'll apply a KVL in this loop. VB is given equal to 0.7 volt. So by applying in this KVL in this loop, by applying KVL in this loop, we can calculate the base current IP. Now when we apply KVL, we get the equation minus 24 volt plus 4.7 kilo ohms into IC plus IB plus 560 kilo ohms into IB plus 0.7 volt equal to 0. We know that IC is equal to beta into IB, so IC plus IB can be written as 1 plus beta into IP. So this equation becomes minus 24 volt plus 4.7 kilo ohms into 1 plus beta into IB plus 560 kilo ohms into IB plus 0.7 volt equal to 0. Now in this equation there is only one unknown, that is IB, which is calculated as 24 minus 0.7 divided by 47k into 1 plus beta. Beta is given 100, so 101 into, sorry, plus 560 kilo ohms. So when we calculate this, we get IB equal to 22.52 microamperes. Now the quiescent collector current ICQ is equal to beta into IP, which is equal to 100 into 22.52 is comes out to be 2.3